Lewis dot diagrams for compounds. Who created the Lewis dot diagram? Gilbert Newton Lewis created the diagram as a way to visually show how many valence electrons an atom has in an easy and effective way. What is a Lewis dot diagram? Lewis dot diagrams are diagrams which illustrate how many valence electrons an element located in the S&P block has. Example shown below. We can represent the valence electrons of an atom using a Lewis dot symbol, in which the element symbol is surrounded by dots representing the valence electrons. For example, oxygen has 6 valence electrons, so its Lewis dot symbol is. Note the 6 dots representing the 6 valence electrons. We can represent the valence electrons of an atom using a Lewis dot symbol, in which the element symbol is surrounded by dots representing the valence electrons. For example, neon has 8 valence electrons, so its Lewis dot symbol is. For example, carbon has 4 valence electrons, so its Lewis dot symbol is. Why are Lewis dot diagrams different for compounds? Compounds must share electrons in order to obtain 8 valence electrons and create a chemical reaction. This creates a different orientation when making a Lewis dot diagram for compounds compared to making one for elements. When nonmetallic elements react with other nonmetallic elements, they share electrons in order to obtain 8 valence electrons. Each fluorine atom has 7 valence electrons. They each require 1 more electron to satisfy the octet rule. The left fluorine atom now has a total of 8 electrons around it. The right fluorine atom now has a total of 8 electrons around it. The shared electrons form a covalent bond. The unshared electrons are called lone pairs. The 2 electrons that form the covalent bond are often represented by a single line. The F2 molecule can be represented using a line of dots to show the bonding pair and the 6 lone pairs respectively. This is called a Lewis dot structure. Some atoms have to share more than 1 electron in order to satisfy the octet rule. Each oxygen atom has 6 valence electrons. They each require 2 more electrons to satisfy the octet rule. Some atoms have to share more than 1 electron in order to satisfy the octet rule. The left oxygen atom now has a total of 8 electrons around it. The right oxygen atom now has a total of 8 electrons around it. The 4 electrons shared by the oxygen atoms form a double bond. The double bond is represented by 2 single lines. Each line in the Lewis dot structure represents 2 electrons. The element hydrogen is an exception to the octet rule. It only needs 2 electrons rather than 8 to be stable. The hydrogen atom has 1 valence electron. It requires 1 more electron to be stable. The fluorine atom has 7 valence electrons. It requires 1 more to satisfy the octet rule. The hydrogen atom now has a total of 2 electrons around it and is stable. The fluorine atom now has a total of 8 electrons around it and is stable. The Lewis dot structure of the HF molecule shows a line and 6 dots to represent the bonding pair and the 3 lone pairs of electrons respectively. Rules for creating diagrams. There are 4 rules when completing these intricate diagrams. These rules help to ensure that the diagrams are executed correctly. Rule 1. Add together the number of valence electrons for each atom in the molecule. For example, CF4. Carbon has 4 valence electrons and each fluorine has 7 valence electrons. Therefore, the total number of valence electrons equals 4 plus 4 times the quantity of 7, which equals 32. Rule 2. Write out the elements of the molecule so that the least electronegative element is in the center, surrounded by the other elements. For example, CF4. Rule 3. Place a covalent bond between the central atom and the outside atoms. Remember, each covalent bond contains 2 electrons. For example, CF4. The 4 covalent bonds use 8 of the 32 electrons in CF4. There are 24 electrons mating. Add electrons to the outer atoms as lone pairs to satisfy the octet rule. This uses 24 electrons. There are no electrons left, so this is the Lewis dot structure for CF4. How do I find the valence electrons of an element? The number of valence electrons varies by element. For the main group elements, the number of valence electrons is equal to the group number that the element belongs to. For example, sodium belongs to group 1A and therefore has 1 valence electron. For example, bromine belongs to group 7A and therefore has 7 valence electrons. References: